Welcome everyone to the Simon Center and this installment of the Della Pietra lecture series. The original purpose of this lecture series and the continuing purpose of this lecture series is to bring world-class scientists to the Simon Center, to the Stony Brook campus, to the North Shore of Long Island. World-class scientists who have an ability to explain the excitement of the work they do to general audiences such as this one. And we're very pleased today to have an exemplar of such a scientist, Frank Wilczek, to give today's Della Pietra lecture. Frank was, well, I should start by saying Frank was born in Mineola, New York, right here on Long Island, so he's one of our own. Local boy made good. He was an undergraduate at the University of Chicago, where I'm happy to tell you that he majored in mathematics. He then went to Princeton to be a graduate student in mathematics, spent a couple of years doing that, and then decided to switch to physics. Now, I'm sure the physicist would tell you that he saw the light. I won't burden you with how the mathematicians would describe this transition. Anyway, he made it, for good or for bad, and in his case it turned out to be for very good, because I believe it was during his first year as a graduate student, he did some work with his thesis advisor, which 31 years later led to a Nobel Prize. Not bad for a former mathematician, if you ask me. Frank has won many, many awards, including the 2004 Nobel Prize. Let me just list a few of them. I could go on and on and on, but let's see. I have to get my glasses to see this. Where did they go? Oh yes, he was a MacArthur Fellow. He won the Dirac Medal. He won the King Faisal Prize. And as I've already mentioned, he won the 2004 Nobel Prize for the discovery of asymptotic freedom in quantum chromodynamics. But the prize that I want to focus on and read the citation from is the Julius Edgar Lilienfeld Prize of the American Physical Society. This is a prize given to scientists for both their scientific work and their ability to explain to a more general, to a wider audience, that work. And the citation reads, "For his role in the development of asymptotic freedom and other aspects of quantum chromodynamics, a cornerstone of the Standard Model, for his remarkable versatility in research in condensed matter and astrophysics, as well as particle physics, and for his outstanding ability to lecture and write with clarity, profundity, and enthusiasm." So that summarizes the two characteristics we look for in a Della Pietra lecturer, and we certainly have them today. So please welcome Frank Wilczek.
Thank you, John. For that very generous introduction. It's good to be home. And I really do feel every time I come to Long Island like it's coming home. So it's very special to be here. Today's talk will be rather different from ones I usually give. However, it's an area that I've increasingly come to be interested in and have been actively working on in recent months, and is close to my heart also philosophically, in that I feel a lot of my more mathematically sophisticated, technical work at the frontiers of physics has really been aiming at the same end in a less direct way, that is, expanding our notion of what reality is and our ability to appreciate it. The motto for this talk is these famous lines by William Blake. And you'll see as the talk develops how deeply relevant they are, and then we'll have some occasion to correct them at the end. William Blake said, "If the doors of perception were cleansed, man would see things as they are, infinite." These lines from The Marriage of Heaven and Hell inspired Aldous Huxley in his explorations in psychedelia, and also inspired the band, The Doors. This is where their name came from. So it's very inspiring indeed. So first let me talk about how limited our senses are very briefly. We really, as we learn more about the world, understand more and more that our unaided senses sample a pathetically small fraction of what's out there. We don't see things that are very small. We don't see things that are very far away. We have very poor resolution when we hear things to tell where the sounds are coming from. Our chemical senses of smell and taste are well below the standards of a chemistry laboratory. And so forth. Our sense of time is very poor. But we've learned to augment our senses in many ways in order to take advantage of these potential aspects of reality that our unaided senses don't see. We use microscopes and telescopes. We use watches. And of course, we use chemical analysis to figure out what's in the substances we look at or even eat. Nevertheless, we've left a lot on the table. I'll be discussing one aspect of that, which is particularly impressive in two ways. First of all, we can be very explicit and clear about what we've left on the table because we know what's out there. The physical nature of the electromagnetic spectrum we understand by now quite profoundly, and we can be very definite about the fact that we're missing a lot. Be very concrete about what we're missing. And some of the very greatest physicists were involved in clarifying the nature of color, light, and the electromagnetic spectrum. This is a graphic depicting, hey, hello, my great aunt and uncle have come. It's lovely. I told you, it's like coming home. I thank you. And Newton is usually thought of as a theoretical physicist, or mathematician even, God help us. But he did experiments. He very much did experiments. And his, perhaps his most famous experiment, which is a profound set of experiments, was to clarify the nature of color. Here he is in his room at Cambridge, putting light through from a little slit in the window through a prism, breaking it up into different colors. This is something that many people had observed before, but it was Newton who really figured out its profound meaning. What he did was take this spectrum of light with the different colors and isolate a particular part, say yellow. Then he found, by just stopping everything else, then he found that if you put the yellow light through another prism, it behaved in the same way as before. It stays yellow, it doesn't break up further, and it bends through the same angle that it originally bent through when going from air into glass. And Newton subjected this purified light to all kinds of indignities, passing it through different kinds of substances, bouncing it off things, and it stayed yellow. So he decided that, or made the case, that the true nature of light is, the true nature of color is that white light is made up of a compound of the different primary colors, the primary substances, if you like, in light are these purified colors. And then he did a crucial experiment showing that you could put together the white light again by combining the spectral colors. The next really major development in understanding the nature of light came in the mid-19th century with the development of Maxwell's equations. Maxwell, in 1864, codified everything that was known about electricity and magnetism at that time into equations. These equations, known as Maxwell equations, you can find on the wall of the Simon Center. So they must be pretty good. Let me see if I can remember how to, whoops. Yeah. They can be written in different forms, which is one aspect of their beauty and versatility. And another aspect of it is that one of the forms is in terms of pictures. The different Maxwell's equations have a geometrical interpretation. One of them, Gauss's law, says that the amount of electric field, the so-called flux of electric field flowing out of a surface, is proportional to the charge inside. Another of them is the same thing for magnetic flux, however, with the additional input that there's no such thing as isolated magnetic charge, so the flux is always zero, as much comes in as goes out. And then there are laws that tell you that electric currents produce magnetic fields around them, and Faraday's law was a relatively new law at the time Maxwell was thinking about these things. Maxwell discovered his so-called law of induction, that if you have magnetic fields that change in time, they produce electric fields. So that's what Maxwell was up against. And when he found that when he put together those laws, they were inconsistent. They were mathematical system of equations was inconsistent. Now, a very good but sub-genius physicist might have stopped at that point, but Maxwell went a step further. He showed that if there were a new effect that hadn't been observed, he could fix the laws and they would become consistent mathematically. The new effect that he postulated was a kind of dual to Faraday's effect. Faraday, remember, said that changing magnetic fields produce electric fields. Maxwell's new effect that he postulated in the absence of experimental evidence was that changing electric fields would produce magnetic fields based on mathematical aesthetics or consistency, if you like. When you add such an effect, something very new happens. The electric and magnetic fields kind of can take on a life of their own. Faraday said changing magnetic fields can produce electric fields. And now Maxwell is saying that changing electric fields can produce magnetic fields. And now they can, one after the other, sort of chase each other and produce a propagating disturbance in electric and magnetic fields. Maxwell was able, from his equations, to calculate how fast such a disturbance would travel, and he calculated that it would travel at the speed of light. So Maxwell, being a bold and clever fellow, said that that is light. Here's what he looked like at the time. You can see the emblem of wisdom here. And he said, we can scarcely avoid the inference that light consists in the transverse undulations of the same medium, that is, these changes back and forth, which is the cause of electric and magnetic phenomena. And to this day, that's our understanding of what light is. It's a disturbance in electromagnetic fields that you can set off by a spark, for instance, as Heinrich Hertz first did, and then it takes on a life of its own and can travel indefinitely. This opens up a new perspective on what light is, but it's more. Because in addition to visible light, which is the electromagnetic fields turning into each other at a certain rate in space, a certain wavelength, if you like, or a certain frequency in time, the equations allow solutions with different wavelengths that don't correspond to visible light. These were unknown at the time that Maxwell postulated his equations, but today we send signals with them, or cook with microwaves, get sunburns with ultraviolet, take pictures with X-rays, and so forth. So visible light is only this little section, even though it's infinite in possibilities. It's a continuum. There are a continuum of spectral colors, as Newton already showed us. It's not only infinite in the sense of a continuum, but infinite in both directions towards long wavelengths, radio, microwave, infrared, and then towards shorter wavelengths, ultraviolet, X-rays, and gamma rays. All that was in Maxwell's equations. This is Heinrich Hertz, who experimentally verified Maxwell's postulated effect, and in the course of doing that, invented what the technology that led to radio and all the other later developments of electronic communication. And before he died at the age of 35, Hertz had time not only to do those experiments, but to say some very profound things, including this, which I think is one of the most beautiful quotations in all of literature, certainly in all of the scientific literature, and very appropriate. I think you'll agree. One cannot escape the feeling that these mathematical formulae have an independent existence and an intelligence of their own, that they are wiser than we are, wiser even than their discoverers, that we get more out of them than was originally put into them. So, very true of Maxwell's equations. So, that's what light is, and how it sits in a larger context of possibilities for electromagnetic radiation. How do we sense it? What part of this do we grasp? Well, Maxwell, again, is the hero of this story. This is a picture of Maxwell at an even younger age. And you'll notice he's holding this funny instrument. This is a color wheel. We'll do an analog momentarily to show the sort of thing that Maxwell was investigating with the color wheel. He was investigating our perception of color. That is, by spinning the color wheel, you could see colors that weren't there in the original wheel and study how different colors mix in human perception. So Maxwell was a hero not only in the physical nature of light, but also in understanding our perception of it, which, as you'll see, is quite different. He later produced scientific instruments to study this more accurately. And I should mention that Maxwell is a hero to a lot of us, but it's not so well known that a large fraction of his published work is devoted to the theory of color perception and color vision, and he did extensive experiments on the subject. In his later investigations, he developed a more civilized and accurate tool than these tops, more dignified than the color tops. which enabled more precise experiments. This is the color box, which the idea is you let in amounts of spectral color and spectral parts of the spectrum that's under your control, and compare it with a known source of light, and you illuminate half of some figure with each of those and see if you can match the given color sample with pure, or the combination of pure spectral colors. By investigations of this kind, which we'll partially recapitulate in a moment, Maxwell and his followers established that mixtures of exactly 3 spectral colors are sufficient to match any perceived color. So, whereas there's a continuum of possible colors, our perception only picks out a 3-dimensional version of that, 3 averages. You can match any perceived color by mixing no more than 3 spectral colors, whereas 2 won't do. So let me show you my first demonstration, which is a sort of version of Maxwell's color box. You can turn down the lights. So here are 3 colors, pure spectral colors: red, green, and blue. Okay, you remember yellow was another spectral color, so there's a pure version of yellow that you can see in a rainbow. But there's another version of yellow, which is impure, but looks the same to us. Watch. If I mix red and green, the mixture of those colors makes a very convincing yellow. And then, if we also allow ourselves some blue, whoops, wrong way, we can make white. And by doing experiments of this kind, Maxwell verified that you could produce any color, any perceived color whatsoever. You could match any perceived color by mixing appropriate amounts, appropriate brightnesses of just 3 colors. Okay. Well, I love this one, so I'll leave it. Making yellow out of, making a fake yellow, if you like, or a non-primary yellow out of green and red. We can make a more, I will turn, another demonstration of this, which leaps to the eye, is this. Here we have a ball, which you'll see is illuminated white. Okay, can we turn down all the color, all the lights? So this is a white ball. The white that you've seen is actually a mixture of the 3 colors. They're slightly out of sync, but not so out of sync that your eye can resolve them. However, when you put them in motion, they're in different places, and now you can see that there were 3 underlying colors to make that white. With some hesitation, let's try to look at Maxwell's top. We had a hard time in rehearsal getting this to work properly. The trouble is that modern cameras do all kinds of averages and compensations so that they don't do justice to our actual perception of light. So you will actually get a better impression of Maxwell's top and how it illuminates the sense of color. If you look at the wheel, it probably will get somewhat distorted if you look at the camera picture. Okay, bikes. Yeah, rotate it. Oh, this is okay. Then you see that depending on the speed at which I make this strobe go, different numbers of the colors are compounded. If you get them in sync, you can see that you're producing quite different colors in perception than were there originally, and they can be stable mixtures. And it's really fun to play with these tops. Maxwell enjoyed it, and so can I, and so can you. Okay, thank you. Much later, in a remarkable development, biologists discovered the reason why you can make any perceived color out of three primary colors is that in the human eye, there are three different proteins that respond with different sensitivity to different parts of the electromagnetic spectrum, take certain averages, and it's by processing the information from those three kinds of receptors that humans produce their color vision. If you lack one or more of these kinds of proteins, which many people do, especially many males, you'll have different forms of color blindness. It's interesting to contrast our sense of color with our sense of sound, or our sense of audition. The way we handle different frequencies of light is quite different from and much cruder than the way we handle different frequencies of sound. As I mentioned, we have three proteins which are photon counters, really. They are all or none, depending on whether they get a burst of energy in the appropriate kind of region of the spectrum or not. Their sensitivity curve is broadly tuned, but nevertheless they're just on or off sensors. Our ears are quite different. Inside our ears we have something called the organ of Corti, which is an extended strip that narrows and thickens towards one end, and it therefore is in resonance with incoming pressure waves. At different parts of it are in resonance with incoming pressure waves at different frequencies, and so this little thing in our ear actually resonates with incoming sounds, and if there are several different sounds of different frequencies coming in, we'll have different parts resonating, and we can therefore put those together, and that's what we sense as musical chords. So although the sense of hearing doesn't have the possibility of making images, it has a much richer frequency sensitivity than our sense of vision. But that analogy allows us to think about what vision could be. If we expanded the doors of perception, instead of just seeing colors, three kinds of lumpen chords that we actually do see, we should hear much richer chords, different ones at each point in space. We could have both images and chords at once, with the aspects of our hearing and the aspects of our seeing. The information is out there. Most mammals, we can ask if other creatures have exploited this possibility. And if we look in among mammals, the humans are actually at the upper end of color perception. Most mammals have very poor color vision. Dogs, for instance, have only 2 color receptors instead of 3. So you can make a model of what Fido is missing out on. So if this is what you see, Fido doesn't see the color highlights that are visible to a human. They've lost some of the color information. Bulls have no color receptors at all. So bulls only see in black and white. The famous use of red capes to enrage bulls is meant more to impress the audience than to impress the bull. The bull just sees the motion of the cape, doesn't know that it's red whatsoever. On the other hand, several kinds of bees, birds, and butterflies, things we might think of as not as sophisticated as mammals, have 4 or even 5 color receptors. And they sense in the ultraviolet, or more rarely in the infrared, not only in what we see as visible light. And then there's the champion of vision, the Mantis Shrimp. The Mantis Shrimp sees not 3, not 4, not 5 colors, but 16. So here's the sensitivity curves of our 3 color receptors. This is the Mantis Shrimp. Has many more. They go into the ultraviolet and into the infrared over here as well. So this is my new favorite animal. This is what they look like. And you can see that they're colorful to be attractive to other mantis shrimps, presumably. The extraordinary visual apparatus of the mantis shrimp raises many fascinating questions for biology. How and when did it evolve? What is the mantis shrimp seeing that's so important to it? How does it process so much complicated information with such a teeny-weeny brain? Let me now show a little video about the mantis shrimp, which to emphasize some of these points.
The mantis shrimp is equipped with powerful claws and powerful eyes, the most complex in the animal kingdom.
You'll notice, by the way,
He
that
can see polarized and ultraviolet light.
on these
10
eyes, which
times
move
more
all
colors
around,
than we can.
it has 3 irises
And he's a
on each
meticulous
one,
creature,
so 6
whether
altogether.
caring for his eyes or keeping his burrow clean. The mantis shrimp is neither mantis nor shrimp, though he looks a lot like both of them. Many of the 400 species of mantis shrimp are armed with special hardened claws. And they're not timid about using them to defend their turf. A mantis shrimp is quick on the draw. A punch takes just 3 milliseconds and strikes with the force of a bullet. With the enemy dispatched, he cleans his eyes so he can watch for the next threat.
Okay, so that's the mantis shrimp. It's quite inspiring in many ways, I think. Besides this continuum of different wavelengths or frequencies or colors, if you like, there's another aspect of light that emerges from Maxwell's equations and has been verified in many, many experiments. And, that, again, our eyes are not sensitive to. This is the polarization of light. Again, this is another thing that bees, some kinds of birds, and the Manta Shrimp naturally is sensitive to. Polarization is a phenomenon that arises from the transverse nature of light waves. That word already appeared in Maxwell's quotation, you may remember. Let's demonstrate what it is and why light has this property of polarization as well as a wavelength. We can demonstrate transverse waves using this spring. Okay, so if I put on a magnetic excitation of the spring, the wave, well, of course, it's a finite length, so this wave bounces back, but it's propagating this away and oscillating that away. So it's oscillating in a direction transverse to the direction of motion. And this is the way also electromagnetic waves behave. In that case, it would be the electric field that's oscillating in magnitude. And it can oscillate, if it's transverse, it can oscillate in a vertical plane, but it can also oscillate in a transverse plane. So it has a polarization. Newton said that light has sides. He thought of lights as particles. He thought that said the particles have sides. This is what he was talking about, that there are polarization phenomena. You can also have mixtures of these two to make circularly polarized light. That's an equal mixture of left and right, of this way and that way. Okay, thank you. So this is another aspect of the richness of reality to which our senses are blind. Nevertheless, there's useful information in it. Let me show you things that you can see if you're sensitive to polarization that you can't see if you're not sensitive to polarization. So here I have a polarizer which lets through one direction of polarization but not the other, of linear polarization. So light waves propagating in one direction get through. If the electric field is oscillating in the other direction, it doesn't get through. It reduces the intensity of the light by 2 if we start with unpolarized, by a factor of 2 if we start with unpolarized light. Now, if we take two of these things and they're aligned so that they are both letting through the same direction of polarization, it's still half the intensity. But if they're crossed, then nothing gets through. Each polarization is blocked out by one or the other. So this is a convenient way of making different kinds of polarization and studying its effects. Now, here you see nothing. There's actually a bit of transparent tape on here, ordinary cellophane tape. If we put it in polarized light, it still doesn't look like much. However, the way in which the polarized light propagates through is distorted by how much of this stuff it propagates through, a phenomenon called birefringence. And if we bring out the polarization after it's propagated through the tape, we see that it has a rich color, rich structure that's color dependent. And this is something that, of course, we wouldn't see without the polarizers, but eyes that were sensitive to polarization would see all this. This is another infinity of reality that we don't sense. We can also look at something perhaps more useful and delicious. Caro syrup looks completely transparent. And again, if you put it through polarization, it doesn't look like much. However, the light that's passed through the Caro syrup has had its polarization rotated. This is an effect called optical activity, depending on the kind of circular polarization that it had. And the amount of rotation depends on the color, and therefore you see different strengths of color and different net colors depending on polarization and depending on how much of the syrup it's traveled through. So this is the sort of thing that mantis shrimps and bees and birds can do automatically, but we have to manipulate these plates and things to try to bring it out. Okay. Thank you. Polarization is actually quite useful, has useful information, not just to demonstrate odd properties of Caro syrup or cellophane tape. For instance, if you sense just one kind of polarization, for instance by putting on appropriate glasses, you can reduce the glare on a very sunny day because reflected light of the sun is strongly polarized, and if you take out that direction of polarization, you get rid of the glare. So polarization doubles the dimension of color space, which was already infinite. Continuous, so infinity and infinite in that way, and also infinite towards longer and shorter wavelengths. And for each of those, we have the additional infinity of polarization. So, there's a lot more out there than is visible to the naked eye. How can we access it? Well, the paradigm for that sort of thing is coding. We take the information in all kinds of forms and code it into a form that's more user-friendly. So this is done, for instance, with infrared sensors and cameras, which are used, for instance, in police work. When you want to see what's going on at night, you wear infrared glasses, and the crooks can't see you, but you can see the crooks. And that's done by having appropriate electronic instruments that change infrared light into this kind of green that we can sense. And you can do more sophisticated things, making different brightnesses of infrared light, turning those into different colors of light, of colors we do perceive. Similarly, we can project the ultraviolet light emitted by objects into colors that we do see. So this is what this particular yellow flower, I don't know what it is, looks like to a human eye. But birds, the birds that fertilize it and the bees that fertilize it see something quite different. They see a structure which is inviting it into the middle where the honey is to do their work. So they see this kind of bullseye target in the ultraviolet, and by encoding ultraviolet as red, we can see, in a sense, what the birds and the bees see. A very remarkable case of ultraviolet vision is the scorpion. The scorpion, I thought this was a really exotic effect, but when I lectured on this subject in Arizona, people told me that everybody knows this in Arizona. What you do is shine ultraviolet light around if you want to find scorpions. Because scorpions, when exposed to ultraviolet light, later very quickly start fluorescing in this kind of blue. Scorpions, with their whole body, sense the ultraviolet light. Scorpions like to hide, and they like to hide even from the light of the moon, which is rich in ultraviolet. So their whole body is sensitive to ultraviolet. If any part of it is exposed to ultraviolet, they feel very uncomfortable and scamper to hide. So they are whole body ultraviolet sensors. This fluorescence is kind of the waste product of their absorption of the ultraviolet light, and then they sense it and give off degraded blue light. So it's certainly possible to sense these additional colors and code them into forms that we can appreciate with our limited senses and unlimited brains. We can synthesize artificially new receptors as physical preprocessors quite easily by procedures related to Maxwell's color box idea. You just sense those whatever combinations you're interested in and encode them as new kinds of receptors, if you like. And you can image with that light, whatever. So I can't tell you exactly the schemes I'm using to try to exploit this information and make it user-friendly, because I'm in the process of patenting them. But I can tell you my philosophy, which is, if Mantis Shrimps can handle it, so can we. So I look forward with anticipation and confidence to seeing more of these potentially infinite dimensions of color space. And modifying or bringing up to date Blake's insight with the doors of our perception expanded, we will get closer to things as they are, infinite. Thank you. Sure, I'd be happy to take questions, right?
Questions?
Excuse me?
Which means that the shrimp reflects red, green, and blue.
Reflects?
Right? Reflects.
Well, it's very colorful, if that's what you mean, right?
So is it very colorful with respect to 16 colors?
Yes. Presumably that's the reason it has these 16 colors, to enable it to appreciate probably sexual displays of other Manta shrimps. So they're seeing some wonderful displays that we are totally lost on us. But we can see, but we can certainly see that they're very colorful creatures. Right? That we can appreciate. Now, since I should make one important statement about the Mantis shrimp. The Mantis shrimp, as we've seen, is sensitive to these 16 different averages of different colors. That doesn't mean that it can synthesize those into meaningful information with anything like the richness that we do with our 3 receptors. So the way I like to say this, and I think that that has been borne out by some recent experiments, is that whereas we see a 3-dimensional space based on our colors, and mixing them in different ways, they see 16 points in the space, but can't really extrapolate and interpolate to make a solid body out of those 16 points. They just sample different templates, if you will. Yes.
Again, on the Mantis shrimp, because the penetration of light into seawater is very wavelength dependent,
Yes.
it must be that you do not find these creatures below a certain rather shallow depth.
That's right. They concentrated on the coasts. A lot of this sophistication would be wasted in the deep water. Right? And presumably there's some price for it. So Yes. Mantis shrimps are extremely successful. As the narrator mentioned, there are 400 species of them. The mystery to me is why they haven't taken over the world, or at least the coastal waters. They have these fantastic eyes. They have weapons. They're obviously very agile. They have armor. They're really quite something. By the way, a lot of people would like to have mantis shrimps as pets. You have a mantis shrimp?
No.
Oh, but they're very difficult to keep as pets because they're so strong and so ferocious. They tend to break aquariums. So unless you have a specially reinforced, strong aquarium, you're going to wind up with a mess of water and mantis shrimp on them. Yeah, exactly, right. So you need special equipment to keep a mantis shrimp. I'm tempted, though, I must say. Yeah.
Sort of on that same subject with red. You mentioned before red and green receptors can have us see yellow, for example.
Yes, we synthesize yellow from.
What would a yellow receptor, let's say, as a shrimp would have, buy you in addition?
Well, if you had a yellow receptor, you would be able to tell the difference between that yellow and true yellow, but we don't. So we can't. So to us, they look exactly the same.
Right.
But if we had another receptor that was specifically sensitive to yellow, spectral yellow, it would fire for spectral yellow. It wouldn't fire for this fake yellow.
Oh, it wouldn't see.
It would not. No. Would not.
Oh.
Yeah.
So one of the sensitivity curves for the mantis shrimp has like 2 peaks.
2 peaks?
Minus peak, I think.
That could be. I mean, proteins are very complicated.
Right. So you think it's
Oh, this one, yeah.
So
I didn't notice that actually. Yeah.
So yeah, I was wondering, what the physics of that could be, and that is evolutionarily significant.
Well, I'm pretty sure it's not known whether it's evolutionary significant. The physics is probably also unknown in detail, but these receptors are big molecules and have different parts, so it's not at all anomalous or extremely peculiar that they might have 2 regions of sensitivity. That is kind of a design flaw, though, because you're throwing in a way.
So if I dream in color, is that a new dimension?
Well, not if you only dream in 3 colors, but if you dream in more. I should mention, by the way, that there are humans, mostly women, a very small percentage, I think like 1 in 10,000 women, maybe 100,000, who have an extra receptor for color, C4 colors. And these women are especially heavily represented among interior decorators and designers. They can see differences between colors that most people can't perceive. Yeah.
When you're discussing how a dog might perceive something, or a bird, or a shrimp, how do you exactly know how they perceive those things?
Well, we infer that from the kinds of receptors they have.
So,
And in some cases from their behavior. So you can do experiments on, train them to get rewarded for seeing something, and then see if you can fake what they're supposed to be seeing with something else, and then you can figure out if they're seeing the same kind of fake yellow that we see, or they insist on accurate yellow, right? And it's that sort of thing that leads you to think that, for instance, the Manta shrimp doesn't process things in anything like the way we do to get a fake yellow, and or recognize that the fake yellow could be in some sense the same as the real yellow. Of course, it isn't the same, so maybe we shouldn't blame it. But well, you get the idea. You can do all kinds of experiments to probe these questions. Yeah.
Yeah.
Are you? Yeah.
Yeah, you.
In terms of the mantis shrimp, if it's not a mantis and it's not a shrimp, what is it?
It's a Manta shrimp. That's just the name. I don't know what makes a shrimp or a mantis, for that matter, but its name is a Manta Shrimp, and I think we should honor that.
There were some pretty definitive color experiments done in the 1960s and 50s using only two colors to produce the entire spectrum perceptually, and these have been well repeated many, many times and so on. Can you comment on that?
I don't think it's possible.
Oh, it's... It was...
Oh, I know what you mean. No, there's another effect, which is if you have certain kinds of colors next to other colors, that can change the perception. But if you just look at color patches, isolated color patches, you need three colors. And that's what
graduate thesis, I did it with isolated color patches, and we saw the colors.
Okay, well, maybe we should talk. Nevertheless, there are three receptors, that's for sure. Yeah. And, you know, in computer screens, everything, all these instruments, where presumably it would be very valuable to do with, to be able to do with two different kinds of illumination instead of three. Everybody uses three. Right.
It's more of a metaphysical question, but do you think if we were born with a different set of perceptions, like this Mantis Shrimp, we would arrive at different fundamental laws of nature? And if so, what does this speak about the ability of current to explain in absolute reality?
Yeah, it's very possible. Well, I don't think that seeing colors different would necessarily do that, because I think we've managed to understand the physical nature of color even with our limited perception. Maybe it would have been quicker. And perhaps one could say the same thing now about dark matter. Some creature that had direct sensory access to dark matter would have in certain respects gotten further in physics than we have so far. Or that was sensitive to microwave radiation and could have seen the microwave sky long, long ago, might have made more rapid progress in cosmology. So yeah, certainly the history could have been very different. Whether the final conclusions would be different, well, I'd like to think not, but I'm not sure.
Sorry. One comment about the light box. Because no two eyes have the same exact proportions of sensors,
Yes.
If you make the same color and match it against the true color for any two different people, it won't be the same mixture. So
That's interesting.
we're looking at you see everything, everyone sees something slightly different.
Oh, that's an interesting observation, but as far as that sounds very reasonable, but as far as I know...
That experiment has been done.
Oh, okay, so people do have slightly different matching curves. But not very different, I don't think.
Well, colorblind.
Colorblind, obviously, is very different, right, yeah.
Yeah. Actually, I was just going to add to his point also, my eyes see different colors, just for me. So. But my question is...
Your two eyes, each of them sees a different spectrum than the other?
Yeah. But my question actually is...
Well, I mean, okay. Have you seen a doctor about that? I mean, one thing that could produce that, for instance, that's simple, and maybe not in your case, is if your lens is not perfectly transparent in one eye, it could change the spectral input.
But, so my question actually is that you showed us ways that we can convert, say, ultraviolet into color that we can see.
Yes.
But that means that we can't then also see color at the same time. So is there a way that we can open a new door without having to close an existing?
Well, that's what I can't tell you about. But yes, there are. Yes. Yes.
Different octaves of the same color.
What's that?
What about different octaves of the same color? Are there creatures which can see
Different objects.
octaves?
Oh, are there? There's no color analog of octaves. No, it's not true that light of double frequency has any special relationship as perceived color as half frequency. That's because the nature is entirely different. It's not a resonant, as I mentioned, it's not a resonant phenomenon. Our response to color is absorption. It's an all or none kind of counting.
So what if we have some device which converts the UV part of the spectrum to sound? Something loud.
Yes.
Can our brain somehow use it as an initial receptor after some training?
Quite possibly, with enough training. But that would lose a lot of information because our hearing doesn't produce images.
One last question. Professor, I do microbiology before I do the study group, and a lot of my friends they do some areas in like applied science, like material science, and all of us have a strong feeling that sometimes it is the system of perception that limited our progress in these applied sciences.
Oh yes, it's quite possible. Yeah. Well, as you probably know. Well, go ahead. I'm sorry.
Repeat the question, please.
Based on the
I'll repeat it.
Sentence of your lecture, of your slides, could you give a hint of the areas that may have a?
Well, I'll tell you examples, existing examples. For instance, another demonstration I thought of doing is a useful tool for analyzing stress patterns in materials. Stress patterns in translucent materials is to put them through this kind of cross-polarized light, and you can see visible where the most strongest stresses are, and so it causes rapid rotation of the plane. So by studying studying things in polarized light, you can see those stress patterns with the naked eye. You can also analyze minerals by taking little samples, and it turns out different minerals also have strong polarization effects, and also very rich spectra. So by studying them in different kinds of light, you can do chemical analysis very quickly and on large amounts of material. So that kind of thing you can certainly do.
Coding, you said in your slides. Thank you.
Yeah, that's coding in the sense of changing stuff that's invisible to us normally into things that we can sense by the same sort of tricks I showed here, just changing amounts of polarization into amounts of intensity. Intensity we can sense, polarization as such we can't sense, but we can change polarization into intensity by putting light through a polarizer. It's as simple as that. And that's the kind of idea that makes these things accessible. Right. So there are many instruments for. Well, just to finish, let me give you a couple more examples about polarization. The Vikings knew about polarization. They had stones that produced different that were birefringent, so they caused different polarizations to separate, and they could see how much of each you had. And they used that to navigate on cloudy days. You can see the direction of the sun because reflection, as I mentioned, produces polarization. And so if you're looking in the opposite direction of the sun, you see a very polarized sky. And the Vikings were aware of this effect and used it.
Clear days.
What's that?
Clear days.
No, on unclear days, because on clear days you can see the sun, but it's useful. It's useful on unclear days because you can see the many times reflected light. You can see the effect through polarization. Well, maybe I should leave it at that. There are many, but there are lots of entertaining examples.
Well.
One thing about working on this is it's really fun. Right.
I certainly learned a lot today. And one thing I learned that I wasn't expecting to learn was why I get into arguments with my wife over color. No. I said the aquamarine dress, not the blue dress. Why did you bring that one? She must have a fourth color receptor.
Well, yes.
Anyway, I learned much beyond that. I think we all did. Thank you very much.
So my great uncle and great aunt are. Can I bring them to dinner? Invite them to dinner? Yeah. Okay.